Let's take a look at our example. And so then what we're going to have in our example is we're going to have a situation where we have a chandelier. It's going to be wired up like this. And I fully understand that looks like an upside down wedding cake, but I'm okay with that. Okay. And then in addition, I'm going to be given this angle, say it's like 60 degrees or something like that. And we're going to be given the mass of the chandelier. And so we'll state that the mass of the chandelier is, I don't know, 200 kilograms or something along those lines. And then the type of question that they will ask us to calculate. So what is the magnitude of the tension force in all three of these wires? Okay. And so if we were to go in and kind of attack this the way we, would have done all the other problems in 4 and 5 so far, we will probably go in and identify, oh, my chandelier is my object of interest. It's the thing with the mass. And then we could go in and indicate the forces acting on the chandelier. And so we would get what forces?
Gravity.
Yeah, gravity. Always a good one to start with. So we're going to go from the center of the chandelier to the center of the earth, which is, locally is down. And then our gravitational force, which very many people refer to as the weight of the object, is going to be equal to the mass times our, 9.80 meters per second squared. And so that's our 200 times our 9.8. This is going to give us 1960, I think, is what we get. Newtons. Okay. So that's the weight of our chandelier right there. And then what other forces do we have acting on our chandelier?
Tension.
Yeah. The wire is attached to the chandelier. And so we will have a tension force. You remember how the tension forces go? What was the rule?
Away from the object.
Correct. It'll go along the rope, cord, string, or chain, and then go away from our object of interest. And so then our tension is going to go up along that vertical wire, is what I was calling them. And so then we mark this with our FT. So, do we have any other forces acting on the chandelier? Y'all are correct. No, we do not. Why? How can we tell? And the one that you usually end up seeing when, students first start is the a normal force. Yeah. So there's nothing else touching the chandelier. Gravity is the only non-contact force, and everything else comes from things in contact with the object. And so the only thing touching our chandelier is that vertical wire, and that's it. So y'all are good. Now that we have all the forces, I always like to then put in the acceleration into I do a force diagram. I don't really do the free body ones because we'll do these ones in 9 and 10. So why would we practice things that we then wouldn't use later on? I don't know. Whatever. But yeah, what you're gonna do is it's a chandelier. It should not be moving, right? So our acceleration should be 0. So it really should be a nice static equilibrium, that there should be no motion on our chandelier. I mean, if the chandelier is moving, probably something's not so great. All right. And then what we can do is we can go in. I have all the forces. We have the acceleration. We would normally pick the coordinate system based off the acceleration. But since there is none, then I can pick anything I like. And so I'm going to go in and I'm going to pick, we'll just make up to be the positive, y direction. And we'll write down our Newton's second law in this y direction for the chandelier. So we have the net force in the y. Now, previously I'd write MAY, and then the next line I'd make it 0, but really the condition here is that it is 0. So we could just start here if you want, or you could do the MAY and make it 0 in the next line. It's 6 of one, half a dozen the other kind of things. So whichever makes you happier is fine. And then let's go ahead and write down our forces. So the tension is up, and I picked up to be positive. So we'll do plus this magnitude of the tension force, and gravity is down, and I picked up to be positive. So minus the magnitude of the gravitational force is equal to 0. And then what we can do is we can move this gravitational force to the other side and solve for the magnitude of the tension force, using Newton's second law. So this becomes our 1960 newtons. Just like that. So we have a tension force going up at 1960 newtons. We have our gravitational force going down at 1960 newtons. Are those third law pairs? Excellent. I do not need to ask you when your birthday was to then tell you mine was the same day to then ask if we were twins. You got it. Yeah, they're different types. It's a tension and a gravity. So yeah, we didn't even make the first condition, much less the on and the by trading kind of stuff. So yeah. Y'all are getting really good at that. So there we go. Now what you would notice is like all 3 wires. I only got the vertical one. What happened? And the answer to this is that we weren't looking at the correct object of interest. You're like, but we drew the object, the one that had the mass, And so the answer to this is that in these equilibrium problems, what we need to consider is what I always call the central connecting object. Okay, so the thing that connects essentially all the wires together is this knot. Okay, and so we actually want to take a look at the forces acting on this, connection point between all 3 wires. And what you get is that we only really have the wires, and we're going to treat the wires as if they're ideal, so we can neglect the mass, and so therefore we don't need a gravity at this, knot or whatever this is. And so then what we'll get is we'll get this, tension force along the vertical wire is going to go down. And then we're going to have a tension force going along this horizontal wire, to the right. I'm going to go ahead and label this as FT prime. And then we're going to have a tension force running along this angled wire up like this. Okay. Now I'm going to label that as FT double prime. But you could call it 1, 2, and 3. I don't care. You call it Fred, George, and Barney for all I care. I just don't want to write all that stuff down. So I want it to be a nice compact notation. Okay. Now, the thing is that if we have an ideal wire, and we almost always make that assumption, then in addition to it being massless and it doesn't stretch, one of the things that we find is that the tension along the wire is transmitted undiminished from end to end. So the tension at this end of the wire is the same as the tension at that end of the wire, okay? And so we would go in and say that, well, this tension up here is going to be our, 1960 newtons. And then this tension here going up was also 1960 newtons. So then that begs the question, are these third law pairs? Manuel says no. Anybody else? Yeah, and Emmanuel points out that there's an issue with the on and the bys. And Emmanuel's correct. This is on the knot by the vertical wire. This is on the chandelier by the vertical wire. Those are not third law pairs. While they are both tensions, the on and the by don't trade. So this is like, I don't know, cousins born on the same day. They're close, but they're not twins still. So, all right, good job. Good job. Probably don't need to ask you anymore about the third law pairs. Seems like y'all have that one down. All right, and so again, we would come in and state that the acceleration on the knot is going to be, 0. And so again, we can't pick our coordinate system to align with the acceleration, but what we can do is pick a coordinate system to minimize the number of components we have to calculate. And so what I would probably do is go in and pick a coordinate system. It would be like vertical and then horizontal, like so. So we'll make this the positive x, we'll make this positive y, negative x, and then, negative y there. Then the tension, this FT tension's in the negative y direction, the FT prime's in the positive x direction, and only the FT double prime are we going to need to find or calculate components for. So we'll need to go in and take a look at that. I'm going to go in and draw out my component triangle. So I'm going to come over like this. And then I'm going to go up like this. But I could have just as well gone up and then go over because they're all the same and it's all fine. Okay. Now, the thing about this tension, this component triangle, is I'm going to need an angle in my component triangle. And Money says it's going to be related to the 60 degrees. Okay. And so what I can do is I can go in and I'm going to use one of my most favorite geometry results. And what we get is that we're going to have this, that if there are two parallel lines cut by a I should have cut my transversal the other way. Sorry. Two parallel lines cut by a transversal, then what we get are, two angles. And the angles have all sorts of names. I don't care what the names are. There's really only two of them. I mean, unless you cut it vertically, in which case there's only one angle, And so what we get is that there's this smaller angle here. 4 instances of that, and then this larger angle here. And there are 4 instances in that. And you get things like, oh, these are vertical angles. These are corresponding angles. These are alternate interior, alternate exterior. I don't care. There's only 2 of them, so let's find them. And so if I were to come in and say that this horizontal ceiling and then this horizontal axis would be cut by this wire itself, then this angle here and this angle here are the same. Those are the alternate interiors. And so now I got my 60 degrees inside my little component triangle. And so then we're going to go in and we're going to solve for this x component of ft double prime, and we're going to solve for the y component of ft double prime. And we're just going to do our standard, stuff we learned in chapter 1, right? And so the problem is that we go, yeah, I'm going to write down the hypotenuse trig function of the angle. And since this one's opposite, it'll be the sine. And since this one's adjacent, it'll be the cosine. And you're like, but I don't know the hypotenuse. I don't know the magnitude of ft double prime. Well, what we're going to do is we're going to write it down as if you do know what it is and just keep on going. This is going to be a lesson for today. Okay. One of the repeating lessons. And so we're going to write down that this is, ft double prime magnitude. And since it's opposite, then this would be, sine of 60 degrees. Okay. And that this x value here would be that same kind of thing. That'll be the ft double prime, but then it's going to be cosine of 60 degrees. And now technically we know cosine of 60 is 1/2, and so you can make it a half, but I'm going to leave sine and cosine of angles in there because it looks more like how physicists normally solve things. They just do it all symbolically to begin with. Now, once we have this, then we can go in and we can write down our Newton's second law in each direction for the knot. So our central connecting object was I'll call it the knot. Okay. This is the thing we need to look at. Okay. And so now what I'm going to do is I'm going to go in and write down, I'm going to start off with the sum of the forces in the y direction is going to be equal to 0 because we're doing a static equilibrium problem. And in the y direction, I'm going to have this ft double prime going up and then this ft going down. And so I'm going to write this as plus ft double prime y component, and then I'm going to do minus the ft is 0. Now on the next line, I'll write down the things that I know. And so here I have this is I don't know the magnitude of ft double prime. This is the sine of 60. I don't really have to write the plus sign because if you drop it, it's the same. So that's usually why I start with the plus one because I'm lazy like that. And then the ft going down, this will be minus our 1960 equals 0. And then now notice that we have one unknown, ft double prime. So we're going to move this to the other side. I'm going to divide both terms by the sine of 60. And this will solve for ft double prime. So then our ft double prime is going to be that 1960 newtons divided by the sine of 60 degrees, which gives us what numeric value? And again, it's a magnitude, so we expect it to be positive. If we get negatives, the implication is our direction's backwards, blah, blah, blah. Y'all got the calculation for me, 2263.2. Seems excellent. There we go. So there's one down. Now we're going to go in and look at the other direction. And so we can write down that the net force in the x direction is 0. And in the x direction, I've got the ft prime. That's in the positive x direction. So we'll do plus ft prime magnitude. And then this x component here on the double prime is in the negative direction. So this is our ft double prime. The x component equals 0 because that's all the forces we have. And so we can put in what we know, and it's like, I don't know ft prime. That's still an unknown. I'm supposed to figure that out. And this is minus, and then this will be my ft double prime, the magnitude. And then this is going to be the cosine of 60 degrees equals 0. And then what we can do is I can take this answer from here and plug it into there. And then we can move this to the other side. Okay. And so then what we get is that our ft prime is this 2263.2 times the cosine of 60 degrees. And then this gives me 60 is half. So this is what 113 1.6 newtons. And there we have it. So yeah. So there we go. And like I said, one of the big lessons is that I didn't know the FT double prime magnitude, but we wrote it down as if we knew what it was and just kept on going with the process. Okay. And it came out in the Newton second law for us. So no. So this particular example is a very simple example of something that, architectural engineers would do or structural engineers would do in order to calculate the tensions in all of the wires. Notice that we have to do this central connecting object. That's the thing that we want to analyze. You will note that we did have to do the chandelier anyways. I mean, without the chandelier calculation, we wouldn't have known this FT tension type of thing. So that had to be done anyhow, but really the object was this like central connecting object type of thing. Okay. And this is important because, that's a 200 kilogram chandelier. I don't know a lot about chandeliers, but 200 kilograms is 440 pounds. That's heavy. That probably means it's also expensive, right? So the last thing you want is don't want the chandelier to come back down once you put it up. I mean, if it landed on somebody, it'd kill them. And you'd know them. It's your house, right? So you don't want that to happen. And so then when you go in to figure out how to wire up the chandelier, then you need to know, well, what wires would you use? Because I'm pretty positive picture framing wire is not going to hold that. But if you use the guy wires to telephone poles, that doesn't look very good. I mean, it won't come back down, but it doesn't look nice. So where in between is it going to be okay? And so this is what those types of engineers would do, is they would calculate the tensions in the wires. They add some sort of safety factor, which might be like doubling it. That's my understanding. I don't actually know. They double the tension and then look for wires that, will be able to withstand that load. And so based on what you make the wires out of and what gauge or thickness the wires come in, then that'll determine, what ones you need to buy. And then it's not done there, because I'm pretty positive that they're going to have to figure out how to connect the wires here. This knot is going to need to be looked at so it doesn't undo. And then, it's attached here at the ceiling, right? They're going to need to worry about this because I'm positive drywall's not going to hold that, because, and if you look at this, the angled wire with the double prime has a tension that is greater than the weight of the chandelier. So if you just bought wires that would hold the chandelier outright, then if you wired it up like this, then it's very likely this angled one will break. So, be careful. You're like, well, why did we angle the wire? I don't know. Maybe that means that this attachment point at the ceiling right here wasn't going to hold the chandelier. So you needed to move it over to here to be where like the joist is in the ceiling. So you could actually get a good anchor on it. Maybe that's the reason. But the chandelier needed to be here, but the attachment needed to be over there. Or I don't know. Whatever the reason is. So there we go. A very, very simplistic example of, something that can be, terribly important kind of stuff.